In the last episode, we ran a sweep across fin count, fin thickness, and fin height, one knob at a time. And we got some good intuition out of it. We understand that thinner fins help a lot. And at the same time, we understand that more number of fins help. And we know height matters less than we actually thought. But here's the problem. We only swept one variable at a time, but the actual best design lives somewhere in the joint space, where all three parameters actually work together in tandem. To find that with a grid search, you'd need roughly 100 runs. At 8 minutes per run, that's 13 hours of compute per iteration. And the really frustrating part, most of those runs would be completely useless. You'd be sampling in corners of the space that are quite obviously bad, just because a grid doesn't know any better. This episode is the theory break. No CFD, just one question. How do you find the best design in 30 runs instead of 100? And the answer is Bayesian optimization. Here's where we are in the series. Episode 2 built the baseline, one case end-to-end. Episode 3 automated it, parametric sweeps across each design variable. And now, episode 4 is the algorithm layer. We are going to understand exactly how Bayesian optimization works before we plug it in. Episode 5 will be the live run, the actual Optuna study, the full automation loop, 30 CFD calls chewing through the search space, and the moment we find the optimal design. Episode 4 is what makes episode 5 legible. Everything in this series, code, notebooks, open form cases, is on GitHub, and you can find the link in the description. Let's be concrete about what we are searching here. 3 design variables. There's n, the number of fins. It's an integer from 3 to 11. T, this is the fin thickness. This is continuous or a float variable from 1 millimeters to 3 millimeters. And h, the fin height. This is also continuous or float from 10 to 30 millimeters. Everything else is fixed. The base footprint, the inlet velocity, and the wall temperature. If you wanted to cover that space with a uniform grid, 5 values per variable gives you 125 different combinations. At 8 minutes per CFD run, that's 17 hours. 7 values per variable gets you 343 runs, nearly 2 days of compute. And a grid doesn't even do a good job. It wastes evaluations in obvious dead zones. The constraint we are working under is budget. We can afford around 30 to 50 CFD evaluations, but that's not enough for a grid. But it might be enough if we are smart about which designs we pick. The insight is that after every run, we learn something. We learn that a design with thin fins and many fins is good. We learn that tall fins don't help much beyond a particular threshold. A smart algorithm should use that information to choose the next design, not just follow a preset grid. That's what Bayesian optimization does. It uses the runs you have to build a model of the objective and uses that model to pick the next run. Every evaluation makes the model better and the algorithm converges. Before any equations, let me give you the whole idea in sort of one breath. Bayesian optimization is a strategy for finding the best input to an expensive function using as few tries as possible. It does that by keeping a belief about how the function behaves and updating the belief every single time it gets a new result. It doesn't follow a fixed plan like a grid. It learns as it goes, and it always spends the next run where it expects to learn the most. And that's the whole thing. Now, why the word Bayesian? It comes from Bayes' rule, which is just a formal name for something you already do every day. When new evidence arrives, you update what you believe. You start with a prior, this is your belief before you've seen any data. Then you observe a result and you combine the two into a posterior or your updated belief. Then that posterior becomes the prior for the next round and you repeat. Think of a doctor. Before any tests, they have a hunch based on symptoms. That's the prior. They run one test, that's an observation. They revise the diagnosis. That's the posterior. They don't throw the old information away and start over. They fold the new evidence into what they already knew. Bayesian optimization does exactly this. But the thing it's forming a belief about is our objective, Q over V across the whole design space. Look at the animation. On the left is the prior. Before we've run anything, our belief is a flat guess with enormous uncertainty. We know almost nothing. On the right is the posterior. After just 3 CFD runs, the belief snaps into shape. It bends to pass through the points we measured, and the uncertainty shrinks right where we have data and stays wide where we don't. That updated belief is the engine of the whole method. Once you have a belief about the objective everywhere, including a belief about how uncertain you are, you can reason about where to look next. So Bayesian optimization is really 2 pieces working together. A model that holds the belief and a rule that reads the belief to pick the next design. The model is called the surrogate. The rule is called the acquisition function. Let's make them one at a time. The first piece of Bayesian optimization is the surrogate model. The idea is simple. From the few design Q by V pairs we have actually measured, we fit a cheap statistical model that predicts Q by V everywhere. Not just at the points we've seen, everywhere. The classic choice is a Gaussian process. A Gaussian process, or GP, gives you 2 things for every unsampled design: a prediction for the objective, the mean, and the honest estimate of how uncertain that prediction is, the standard deviation. Here's what that looks like visually. The blue line is the GP mean, our best guess for Q by V at every point in the design space. The shaded band around it is the uncertainty. Right at the measured points, the red dots, the uncertainty collapses to 0. Far from measured points, the band widens. The GP knows what it doesn't know. And here's the direct link back to that prior and posterior idea. The GP mean plus its uncertainty band is the posterior belief we talked about. Before any data, the GP is the prior, a flat mean and a huge uniform band, the same wide, ignorant guess we saw on the left of the animation. Each red dot is one piece of evidence. The moment we add it, Bayes' rule pulls the mean toward that point and collapses the band around it. A Gaussian process is simply Bayes' rule applied to an entire function at once instead of a single number. That's the key property. A grid search has no model at all, it's just evaluating blindly. But the Gaussian process gives us a cheap, differentiable, probabilistic map of the entire design space after just a handful of evaluations. In the companion notebook, we implement this from scratch, about 15 lines of NumPy. A squared exponential kernel, a Cholesky solve, mean and variance. You don't need to understand every line, but it's worth knowing the whole thing fits in a function you could write by hand. The notebook is in episode 4 Bayesian optimization in the GitHub repo. It renders with all the outputs on GitHub so you can read it without running anything. So we have a surrogate. It tells us for every unsampled design, a predicted Q by V and an uncertainty. Now we need to decide which design should we evaluate next. The naive answer is pick the design with the highest predicted Q by V, but that's too greedy. The model might be confidently predicting a peak somewhere, but if you haven't sampled nearby, that prediction could be completely wrong. We need to balance exploitation. Sampling where the model thinks it's good with exploration. Sampling where the model is uncertain because there might be something even better there. The tool that does this balancing is called the acquisition function. The simplest version is upper confidence bound, or UCB. For every design, compute mean plus kappa times standard deviation. The parameter kappa controls the trade-off. Low kappa, exploit heavily. High kappa, explore more. The design that maximizes this sum is what we run next. What makes this elegant is that uncertainty itself becomes a reason to sample. A design that the model is very uncertain about gets a huge bonus, even if its predicted mean isn't amazing. Once we run it, the uncertainty collapses and the next acquisition will point somewhere else. UCB is the easiest acquisition to picture, but the one you'll meet most often in the literature is expected improvement, or EI. Instead of weighted sum of mean and uncertainty, expected improvement asks a sharper question. Across all the ways this design might turn out, what is the expected amount by which it beats the best result so far? Same job, balancing exploration and exploitation, just a more principled approach. Hold on to the name expected improvement. It comes back when we get to the actual algorithm Optuna will run. In the notebook, we plot the acquisition function alongside the GP posterior. You can see the peak of the acquisition isn't always at the peak of the mean. It shifts towards regions where the GP is uncertain, and that's exploration. Put it together and you get the Bayesian optimization loop. Start with a few random designs, maybe 5 to see the surrogate. Then we fit the Gaussian process, then we maximize the acquisition function to find the next design to try. Next we run the design through CFD, we add that result to the dataset, we refit the Gaussian process, and this whole loop sort of repeats. In the notebook, we step through 3 iterations. Iteration 1, we have 3 initial samples which have wide uncertainty. The acquisition actually points to an unexplored region. It says explore. Iteration 2, we've added that point. The model sort of sharpens near the data. Now the acquisition points closer to the predicted peak, a mix. Iteration 3, the model is now converging, exploitation dominates, and we're homing in on the true optimum. The beautiful thing is that the algorithm is adaptive. If the first few runs happen to cluster near the optimum, it converges quite quickly. If they don't, exploration naturally pushes new samples into uncharted territory until it finds the good region. Either way, every run is useful. The notebook animates this across 3 panels. Watch the gray dashed line. That's the true objective we're trying to find. The algorithm doesn't see it, it only sees the red dots. But by iteration 4, the GP mean is already tracing it closely, and the next suggested sample is right on top of the peak. Here's where I need to be honest with you. The algorithm I just described, the Gaussian process, surrogate plus the UCB acquisition, is the textbook version of Bayesian optimization. It's beautiful and it's instructive, but it's not exactly what we're running in episode 5. Optuna, the library we use, defaults to a sampler called TPE, or Tree Structured Parson Estimator. It achieves the same goal, smart, budget-aware sampling, using a sort of different mechanism, one that scales much better to high dimensions and handles mixed types, integers plus continuous, without any special treatment. Let me unpack that name because every word in it earns its place. Start with Parson Estimator. That's just a fancy historical name for kernel density estimation. Instead of fitting a smooth function through your data the way a Gaussian process does, you estimate a probability density directly. The recipe is almost childishly simple. You take every point you've observed, you drop a small smooth bump, a kernel, on top of each one, and you add all the bumps together. Where your observations cluster, the bumps overlap and the density is tall. Where you have no data, the density is near 0. That sum of bumps is the density estimate, no matrix solve, no kernel tuning. Now, tree structured. TPE can model search spaces where some parameters only exist depending on the value of others. Those conditional dependencies form a tree. We don't need the structure for the heatsink, our 3 variables always exist. But is the reason TPE is the default choice for messy, real-world search spaces like neural network hyperparameters. Now, the actual mechanism. After you've accumulated some results, you sort every trial by its objective value and split the history in 2. The best gamma fraction. Gamma is typically the top 10 to 25%, goes into the good group. Everything else goes into the other group. For our study, imagine we've run 20 trials. The 5 best Q over V designs go in the good pile, the other 15 in the rest. Then you fix one density to each pile using that bump summing trick. I of x, the density of good designs, and g of x, the density of everything else. Here's the intuition made concrete. I of x is tall in regions where good designs live, thin fins, many fins, etc. G of x is tall where mediocre designs live. So a promising new candidate is the one that scores high on I of x and low on g of x. It looks like the winners and unlike the losers. And the natural score for that is simply the ratio I of x divided by g of x. Now the part that ties this whole episode together. That ratio isn't an arbitrary heuristic. TPE is constructed so that maximizing I of x over g of x is mathematically equivalent to maximizing expected improvement. The single most widely used acquisition function in all of Bayesian optimization. Expected improvement asks a precise question. For a candidate design, what is the expected amount by which it will beat the best result we've seen so far? The classic GP approach computes that expectation from the GP's mean and variance. TPE gets to the very same acquisition through densities instead. Same target, expected improvement, two different routes. That's why TPE is genuinely Bayesian optimization and not just a lookalike. So how does it actually pick the next design? It doesn't optimize a function over the whole space the way the GP version does. It cheats cheaply and cleverly. It draws a big batch of candidate points straight from I of x, the good density, so the candidates are already biased toward promising regions. Then it scores each candidate by the ratio I over g, and it keeps the one with the highest ratio. That's the next design to run. No gradients, no inner optimization loop, just sample score, pick the best. Two more practical notes. First, TPE needs data before it can split anything, so the first several trials, 10 by default in Optuna, are drawn at random to see the two densities. Only after that does the good versus other machinery switch on. That's exactly the explore then exploit pattern we saw in the loop, just enforced by the startup trial. Second, and this is why we chose it for the heatsink, n, our fin count, is an integer. A Gaussian process would need a special kernel to handle a discrete variable property. TPE doesn't care. It treats integers and other data types, these categories, by building a simple histogram style density instead of a continuous one. Mixed integer and continuous spaces just work with zero extra configuration. The default Optuna sampler handles our problem out of the box. The notebook has a visual for this, the I of x and the g of x curves. The ratio and the arrow pointing to the next candidate is the same shape as the UCB acquisition, a peak somewhere in the space, just computed through a fundamentally different mechanism. Before we point this at the heatsink, two honest questions. Why this particular tool and where does it fall down? Because no optimizer is magic, and if I don't tell you the limits, then I'm obviously selling you something. First, why Optuna and TPE? 4 reasons, all practical. Number 1, it handles our mixed search space out of the box, an integer fin count and 2 continuous lengths or floater variables without requiring any special setup. Number 2, the study is resumable. It writes every trial into a small SQLite file. So a crash at trial number 12, number 13 costs us nothing. You don't need to restart from trial number 0. You just continue from wherever it stopped. 3, it has a built-in pruner. In that, it can kill a hopeless trial, let's say an invalid geometry, and before we ever even push it to the CFD run, the algorithm understands that this geometry itself is invalid and it just stops there. Number 4, the defaults are genuinely quite good in that we are not hand tuning the optimizer to optimize the heatsink itself. That would just move the problem. Now the shortcomings, and these do matter. First and the biggest, Bayesian optimization gives you no guarantee about finding a global optimum. Instead, it is a smart heuristic. It's not really a proof. it can settle into a good region and stop looking elsewhere. We reduce that risk with random startup trials and enough of a budget, but we never fully remove it. Second, it needs enough evaluations to be trustworthy, in that the belief is only as good as the data behind it. With 3 or 4 runs, the surrogate is basically guessing. So our 30-ish runs is a reasonable budget for 3 variables. However, push to 10 or even 20 variables, the same budget would be far too thin. So the number of runs that you would want to start with increases proportionally here. Third, it assumes the objective is reasonably clean. If a CFD run hasn't fully conversed and reports a slightly wrong Q over V, the model treats that noise as signal and can chase a mirage. So garbage in, confident garbage out. Fourth, and the one that people forget, the optimizer can only ever be as good as the objective behind it. We are optimizing Q over V from a steady simulation with a fixed wall temperature. That's a deliberate simplification. It's cheap and it's fair for comparing designs, but it is not the full physics. Which is exactly why we won't just stop at the optimizer's answer. In episode 6, we take the winning design and put it through a conjugate heat transfer analysis, a real solid conduction, a realistic thermal boundary condition, and no fixed temperature shortcuts. If the 87% gain survives that harder, more honest test, then we will believe it. At the same time, we will also correlate with a lot of empirical models and try and understand where exactly our model sits and if the results are actually believable. Optimization essentially proposes, but validation is the one thing that disposes these proposals. So this episode is proposing, episode 6 will be the disposing. Let's map this onto a specific problem. Our objective is Q over V, heat dissipated per unit volume. Each evaluation is a full CFD run, block mesh, snappy X mesh, buoyant simple foam. About 8 minutes on the VM. That's our expensive black box. Our search space, n from 3 to 11, is an integer, t from 1 mm to 3 mm is a continuous variable, and h from 10 to 30 mm is again a continuous variable. That's the space Optuna's TPE will sample. In episode 5, we'll run 20 Optuna trials. TPE starts with a few random samples to seed the model, then starts making the informed suggestions. The study is resumable. If it gets interrupted, we pick up where we left off, and we have manufacturability constraints in place. This is, the fin spacing has to stay positive and the aspect ratio has to stay reasonable. The result, and I'll show you in episode 5 how we get there, is a design with 11 fins, a fin thickness of about 1 mm and a fin height of 23.7 mm. That design achieves a Q over V of 2.019 watts per cubic centimeter. That's 87% better than the baseline. Thermal resistance drops from 2.03 to 0.93 Kelvin per watt, more than half the thermal resistance gone. And a bonus result from the FANOVA analysis after the study, fin thickness accounts for 67% of variance in Q over V. Fin count is 25% and fin height barely matters, that's 8%. If you had to pick one thing to optimize, it's making the fins as thin as your manufacturing process will allow. The notebook for this episode is in the repo right now. It runs with only NumPy and Matplotlib. Open it, read the cells, run the plots. The whole theory fits in about 100 lines. In episode 5, we wire all of this up for real. The Optuna study, the automated loop, the SQLite database that makes the study resumable, the pruner that kills bad runs early, and the moment around trial number 15 where algorithm finds the thin fin regime and the objective sort of starts to converge. If you've been following this along, you understand the baseline, you understand the sweeps, and you now understand what the algorithm is that I'm talking about. Episode 5 is where essentially all of this comes together. And as always, the code is on GitHub. The link is in the description. If you have any questions, you can leave a comment, and I'll see you in the next one. Keep your residuals low.